Hello everyone, welcome back to the SWAM NPTEL course on engineering aspects of biofuels and biomass conversion technologies. I am Professor Ijaz Ahmed, currently assistant professor in the Department of Chemical Engineering at IIT ISM Dhanbad. In module 7, we are discussing about the low temperature conversion technologies, and in the previous lecture we already discussed about different types of low temperature conversion technologies that includes chemical conversion and biological conversion. Primarily, we are discussing about the chemical conversion technologies, out of which we saw that catalysis is a very important part. So, in lecture 2, we will discuss about catalytic processes for biomass conversion. Although whole low temperature conversion process is about the catalysis, but we will discuss that what sort of catalysts are primarily required for converting the biomass at low temperature into the high value chemicals, fuels and additives, etc. If you remember, in the previous class we discussed about different low temperature and high temperature technologies for the biomass conversion. Okay. Now in low temperature technology we saw that there is biological process and then there is a chemical process. Okay. Now our concern is about chemical process. So whenever we use a chemical process, we use a catalyst. Okay. Now herein we are going to discuss about the catalytic processes that actually affects the whole biomass chemistry and the product, and the applications for low temperature processes. If we see that if we make the glucose, we can get bioplastic from the vegetable oil using a suitable catalyst. We can make the biodiesel or fatty acid methyl ester. We can make HCl biocrude and upgrade it to the liquid fuel, or we can make other value products, but the challenges are with the catalyst poisoning, regeneration and scale up issues. Okay, so this we already discussed and we'll be discussing in this class. So I was going through a very beautiful research article by some of the prominent scientists in the world, and I found that if we look at, this is my lignocellulosic biomass, this is non-lignocellulosic, and here is also, like you can say, animal waste. Okay, non-lignocellulosic biomass. So in lignocellulosic biomass we have hemicellulose, cellulose, and then we have lignin. So if we have to work with lignocellulosic biomass, we just don't need one catalyst but a series of catalysts. Okay, that series of catalysts, for example, the hemicellulose, firstly we use Bronsted acidity to depolymerize it to convert into the maybe xylose, pentose or something like that. Then we use a Lewis acidity for its isomerization. Same thing in cellulose. We use Bronsted acidity to make C6 sugar like glucose, and then we need a Bronsted acidity to convert that glucose into the fructose, which is just a isomer, via the isomerization reaction. So wherever we need dehydration, so Bronsted acidity means if we need dehydration, it's a high strength acid, so we need Bronsted acidity. But if we need isomerization, we need Lewis acidity. I told you, when we need hydrodeoxygenation or we need hydrogenation, then we need noble metal, or you can say metal catalyst. This paper was published quite long back ago in 2016. You can refer to the original source here. But essentially what is needed is a catalyst. Then second, what kind of catalyst and for what purpose? So I said, for example, if you have to go for dehydration or depolymerization, you need a Bronsted acid catalyst. If you have to do isomerization reaction, you will have to go for Lewis acid catalyst. So one thing is for sure, that what we need essentially is a catalyst. Now what kind of catalyst? As I was saying, that it depends on whether we want to go for dehydration or depolymerization as well, or we want to go for isomerization. We can use either Bronsted acid or a combination of Bronsted acidity and metal catalyst to convert into the alkane. Okay, now that happens via the hydrodeoxygenation. Bronsted acid does the depolymerization part. So I would say the Bronsted acid does the depolymerization and this does the hydro deoxygenation part. Okay. And then once it is depolymerized and I mean the ring is opened maybe and we have deoxygenated it using the hydrogen, then what we are left with? The alkanes. And alkanes are again can be used directly as a fuel or we convert it to the bio-oil. So when we have bio-oil and we use the Bronsted acid to remove the OH group from there for dehydration and what we get is the aromatic. We can use this lignin, Bronsted acid, to produce the methoxyalkyl phenol and then we can use further Bronsted acid to produce the alkenes. Okay. Now, similarly, if I go for C6 sugar, I use a Bronsted acid to depolymerize. This is, you can say, here, depolymerize. And here, isomerization. And what I get is 5-HMF again using once. So this is like you can say glucose, then you get fructose. From when fructose is dehydrated, you get 5-HMF. When it goes under dehydration or rehydration, we get the levulinic acid. Okay. But if we want to, let's say, hydrogenate it, we want to make polyols or the sugar alcohol, then what we need is a metal catalyst like hydrogenation or hydrodeoxynation. In both the cases, we need a metal catalyst. Now there we can use the metal catalyst to produce sugar alcohol. That is particularly we will talk about the artificial sweeteners and the sugar like xylitol and the sorbitol. Okay. For example, we can use metal catalyst for oxidation reaction. Okay. And we can get the FDCA, which is not mentioned here, but I'll show in the next reactions, next slides somewhere. Now, in similar way, we can have the algae and animal waste. Okay, you can see. Now, this is rich in lipid, so we can use again acid catalyst, particularly the Bronsted acid, to produce glycerol, or we can use a acid catalyst and then we can do hydrodeoxygenation using the noble metal catalyst to produce the alkanes, or we can use a metal catalyst here to convert this glycerol into trioses that can eventually lead to alpha hydroxy gamma beta-lactone. Okay, or it can produce lactic acid if we use a Lewis acid plus Bronsted acid again, or we can make branched fatty acids by using just Bronsted acidity. So what I mean that there is a whole range of catalysis involved in low temperature biomass conversion technologies. So when we talk about low temperature biomass conversion technologies, there is a whole range of catalyst involved and there are different catalytic processes which are we have to do. Similarly, in case of animal waste, like we have amino acids, we have turpentine, we can use Bronsted acid to make amino acid esters or pinene, etc. Okay. Now then the question is, what are the properties that we should look into the catalyst? So I'll discuss when I'll take the example of the product, I'll discuss again about the catalyst in detail. But herein, let's say zeolite is one of the most used catalyst for biomass conversion. And the factors that matter here is, the one thing is definitely we start with the structural stability and then we have to look at the porosity, we have to look at multifunctionality, whether we need a multifunctional catalyst or we just need Lewis acidity or we just need Bronsted acidity, and then we look at the self selectivity. Okay, so this is a kind of a structure property correlationship depending on our requirement. So it is not necessary that in every process, every catalyst, the noble metal will be there, the Bronsted acid will be there, or the Lewis acid will be there. No, we can have only a metal catalyst doped on some support, or we can have just Bronsted acid catalyst, or we can have just Lewis acid catalyst, or we can have a combination and we can make a multifunctional catalyst. Okay, so that depends. I mean, the catalyst selection is a very important part, and it is very important to understand the structure property function. But because this is a course more on biomass, I will rather focus on the examples of the catalyst, that how they are used, rather than going into the property structure relationship of the catalyst. So some examples I'll take, that where do we need only Bronsted acidity, where do we need only Lewis acidity, where do we need multifunctional catalyst. So for example, if you look at the glucose conversion into the value added chemicals like DMF, levulinic acid and formic acid. The primary reaction that is happening here is the glucose isomerizes to fructose. Okay. And this is a reversible reaction. Now, when you have to go for isomerization, I told you that what we need is Lewis acid catalyst. Okay. Now, when I have to go for dehydration, what we need is Bronsted acid catalyst. Okay. Now, let's say if my end product is only fructose, then I don't need Bronsted acid at all. But if I want to make end product 5-HMF, I need a Bronsted acid catalyst. And if I want to make DMF, which goes through the hydrogenolysis, then I need again a metal catalyst here. So that makes a multifunctional catalyst. Okay. Or I can produce via rehydration. Again, Bronsted acidity is good enough for that. Levulinic acid and formic acid. Okay. Similarly, we can make p-xylene from the glucose via dehydration. So dehydration, I told you, what it needs is Bronsted acidity is primarily, but this will dehydrate to HMF only when there is Lewis acidity. Otherwise, first glucose had to convert to fructose. There may be a route where the glucose doesn't convert to fructose at all. So that we will discuss in coming lectures. So let's say here you need Bronsted acidity to convert into the HMF. Okay. Now that via hydrogenolysis converts to DMF, that means you need some metal catalyst here, and then you have ethylene addition, which is a dehydration reaction. Again, you need Bronsted acid catalyst. Okay. Similarly, we can have only isomerization reaction, like you can see here. This is glucose is converting to sorbose, fructose or mannose. Now what it needs? It doesn't need Bronsted acidity. If I say Bronsted, it doesn't require. When I say metal catalyst, it doesn't require. What it requires is only Lewis acidity or Lewis acid catalyst. Lewis acidity. Okay. So what I mean, that depending on that what kind of end product you need, the catalyst can be a single Lewis acid catalyst, or it can be Bronsted acid catalyst, or it can be a multifunctional catalyst including of metal, or it can be Bronsted Lewis together, it can be metal and Lewis acidity together, it can be metal and Bronsted acidity together, it can be metal, Bronsted and Lewis acidity together. Okay. Now with the monofunctional catalyst, if we have a multiple pot reaction, what will happen? Initially reaction 1 will happen, then product 1 will form, product 1 will go under step 2. Okay. Now in this, because the reaction is happening one after one, so it will take time. But if I have a multifunctional catalyst, I can skip these 2-stage label. I can directly go from reagent 1 to product 1, product 2, or I can go by further product 2 directly. I don't have to make the product at all if I have a multifunctional catalyst, because everything will happen on the surface of the catalyst itself at the same time. So I can avoid the multiplicity and the time consumed, because unless here, if I look at in this reaction case, let's say if this rate is slow, under any condition this product 2 will not form faster. But what if we can, let's say we make a catalyst that can reduce it to single reaction, but again product 1 and 2 are formed. But if my desired product is product 2, why would I form product 1? Then I can go for a multifunctional catalyst. I can make product 2 in one step. And then I'll be able to save my time, money, as well as the chemicals that otherwise will go as a vein as product 1. So the catalyst selection is very important for high value chemical production from the biomass. This is something we'll keep discussing again and again. For example, if you see here, the hemicellulose, it is converted into xylose and then xylose to furfural via a series of like catalysts. Now this furfural, if we have to convert into the furfuryl alcohol, we need a Lewis acid catalyst. And furfuryl alcohol is converted to lulinic acid or butyl levulinate. Then we need Bronsted acid catalyst. And this butyl levulinate actually is converted to the again 5-hydroxy pentanoate that requires Lewis acid catalyst. And this 5-hydroxy pentanoate is converted to the gamma valeriolactone that would require some other kind of catalyst. So what I mean that if you will see, there is a variety of permutation combination that happens in the biomass catalysis. Okay. And this is very important to understand if we want to discuss about the low temperature conversion technologies, that what sort of catalyst are required for what kind of product. And we need only one type of catalyst, or we can have two type of catalyst, or we can have multifunctional catalyst. Okay. Now I'll go into the further detail of this, as I said, that how it happens. So let's start. This is my biomass. Now from this biomass there are three components. Okay. So I have cellulose, and then I have hemicellulose, and then I have lignin. Okay. Now the cellulose, if I do acid hydrolysis, I said for depolymerization, okay, the cellulose will break down to C6 sugar. That means if I want to deconstruct this cellulose into C6 sugar, I need acid catalyst that will convert to glucose. And I want to produce, let's say, fructose. Then what I need is a Lewis acid catalyst for isomerization, as I was saying. And this fructose, if it undergoes dehydration reaction, it will form HMF. And for dehydration, I told you what we need is Bronsted acidity. Okay. So then we will have Bronsted acid sites here. Now, let's say after Bronsted acidity, HMS is formed, and still we want to make something else, and we have Bronsted acid site. Then this can further undergo another reaction to form the lulinic acid. Okay. Now lulinic acid again is a platform chemical, and it has very high value usage. It can be used to produce a wide range of 20 to 30 chemicals for fuel, biopolymer, medicinal applications, etc. Okay. Now, let's say, so here you understand that this route, if I go on this route, what essentially it requires is a combination of Bronsted plus Lewis acid catalyst. Okay. Now, let's say if I have to make these products like sorbitol, which is artificial sweetener, or glucaric acid, we are talking about C6 sugar, or we have to make FDCA. Okay. Now, the sorbitol is produced from glucose via hydrogenation reaction. You can see H2 is added here. And I said for H2 what you need is a metal catalyst. Similarly, the glucaric acid is produced via oxidation reaction from the glucose. Okay. What it needs is a metal catalyst. So if I have to make any of these two products, I would say that like it goes like this from biomass, like this. What it requires? Bronsted acid plus metal catalyst. Okay. Now you see the Lewis acidity is not required here at all. Similarly, if I have to make FDCA, what it requires? the HMF converts to FDCA via oxidation reaction. And for oxidation, I told you here that we require metal catalyst, so we will require metal catalyst. So if I have to make this product and I have to design a catalyst for that, what I'll have to do is, so let's take from here to here. Right? Now you see Lewis acid, Bronsted acid plus metal catalyst. That means if I have to make this product from biomass, directly from the biomass, what I need is Lewis acidity, Bronsted acidity, and a metal catalyst. That means what I need is a catalyst that has combination of this. That means I can say multifunctional catalyst, multifunctional catalyst. Okay. Whereas if I, let's say, if I directly start from like this one, I said the glucaric acid and the sorbitol. What we needed for this? Only Bronsted plus metal. That means it's a, like we can say, bifunctional catalyst. When my product was just glucose, what I needed was just Bronsted acidity. That's all. So this is how we select the catalyst for any reaction. Similarly, for C5 sugars, so here I said that we have this biomass, we have hemicellulose as well. Hemicellulose. Out of that hemicellulose, let's say C5 sugar comes here, C6 will go here. So C6 is a major component that comes here. Now, if I have to make furfuryl alcohol, or let's say if I have to make furfural, which is one of the platform chemicals that is used to make high value chemicals, several high value chemicals and products. Okay. So then what I need, the C5 sugar converts to xylose. This converts to xylulose in the presence of a Lewis acid via isomerization reaction. And xylulose converts to furfural in the presence of a Bronsted acid via dehydration reaction. That means if I have to make furfural only, what I'll need? If I have to make only furfural, I will require Lewis plus Bronsted acidity. Okay. Now, how much that, which product will form, that will depend on my Bronsted to Lewis acidity ratio. Okay. But if I have to make furfuryl alcohol, this happens via the hydrogenation reaction. Now I said in the beginning that if we have to do hydrogenation, what we need is a metal catalyst. That means if I extend it from here to here, this catalyst is not going to work. Why? Because it do not have metal. So what we need for inclusion of this product is a metal plus Bronsted plus Lewis acid catalyst. Okay, that makes it a multifunctional catalyst. Now, similarly, if I take the xylitol, which is sugar-free sugar, we call it, it is again a very high value chemical. I'll discuss. So it requires metal catalyst because it is produced via hydrogenation. Like we make sorbitol from glucose, we make xylitol from xylose. That means if we want to make this also, then it requires here the Bronsted acidity, Bronsted plus metal catalyst, because we are not going to xylulose, we are making directly from here. But if we try to produce xylitol from the xylulose, then we will have to take the Lewis acidity into the consideration. Okay. So this is all about the high value platform chemical production from the biomass and the kind of catalyst that we require. And we'll discuss, we'll take up some of the examples of the high value chemicals, or we'll take like the fuel additives like green gasoline, green diesel additive, and then we have sustainable aviation fuel, commonly referred as SAF. As an example here, we'll discuss what kind of catalysts are needed for that kind of processes. But let's say, why do we call xylitol as a high value chemical or platform chemical? So if you look at the xylitol, this is xylitol. If you don't know what is xylitol, the people who have diabetes, they take these sugar pills, sugar cubes, which is sugar-free sugar. That is xylitol actually. Or if you go and see like the Happy Dent, I was just seeing in the market, and I saw the sugar-free Happy Dent, xylitol containing Happy Dent. Okay, so that is very common. You may be using it, but you have not noticed it. So that is xylitol. This xylitol is not just sugar-free sugar. It's not just a sweetener or artificial sweetener. It can be used to produce ethylene glycol. It can be used to produce propylene glycol. It can be used to produce xyluric acid, lactic acid, or glycerol. Now, this has application in polyester, resins, anti-freezing agents, sequestering agents in detergent builders, building block chemical, textile, food, and cosmetics. Okay. Besides that, xylitol has applications as artificial sweetener, as I said, in oral health product. Oral health, when we say like mouthwash or like there are several sprays, syrups, nozzles, nutraceutical, pharmaceutical, cosmetic thickener, emulsifier, laxative, coatings, mouthwash, toothpaste. So you can see that what you can make from the biomass and how much worth it is. For example, if I say this artificial sweetener from the lignocellulosic biomass and then other high value product that I have showed you, the global market as per 2024 is approximately 1.15 billion. And most of this is produced by the Chinese companies and the DuPont. Some part is by DuPont. I guess 85 to 90% is produced by the China. And that creates a lot of business opportunity in India as well to produce. We can make xylitol from the biomass or the biorenewable resources or biomass derived molecules easily. Okay. And the reason I am saying is because according to the market research, the future estimates around 2.04 billion just in next 10 years. It will double. And why it will double? Because it has usage in the food and beverage industry, which uses the xylitol highest among all the sectors. Then we have pharmaceutical, USD 0.45 billion approximately. It has usage in oral care. It will have usage in dietary supplements. It will have usage in cosmetics and personal care. So you can see that there is a lot of products that can be made from xylitol, and this is only one of the products. Okay, so this is all for the today's class. See you in the next class. Thank you.